test 2. So I'd already answered this. I just want us to revisit this question. There's some other concepts that I need us to have to be able to answer it accurately. So some things we need to know is, let's start with aromatic compound. For a compound to be aromatic, the first thing is it has to be cyclic. The second thing is that it should have no sp3 hybridization, meaning that it should be either sp hybridized or sp2. And the meaning of that is that it should not have only single bonds bonded to four different things. Okay. And then the other thing we need to know is that the bond should be conjugated, meaning that there should be, if you have got a single bond, a double bond, a single bond, a double bond, single bond, double bond, like that. The other thing we need to know is that our molecule should be planar, meaning that it should be in 2 dimension, 2D, and not in 3D. Okay. And then the other thing is our molecule should obey Haeckel's rule, which is 4n plus 2. This has to do with the pi electrons. And then we also have anti-aromatic compounds. Now for anti-aromatic compounds, they also should be cyclic. They also should should either be sp or sp2 hybridized. They should also have conjugated pi bonds. They should also be planar. But the difference is that for them, they don't obey Haeckel's rule. The Haeckel we're talking about is here, meaning that their pi electrons is given by 4n. Now we also have non-aromatic. So if any one of these rules that you've named here has been broken, then definitely our compound is going to be non-aromatic. So if you have got something like this, even if you can see the bonds are alternating or it's conjugated, but it's not cyclic, so meaning that this one is non-aromatic. That's the first thing we need to understand. Let me just do some few examples and then we get to proceed. Let's say we have got a molecule like this one. Which has got 6 carbons. So already we have already mentioned what the formula has to be if something has to be aromatic, 4n plus 1. So try to put where there is n, you put 0. So meaning that the pi electrons should be either 2. If you put where there is 4, you put 1. I mean where there is n, you put 1. It will give you 6 as the value. Where there is n, if you put 2, that is going to give you 10. Where there is n, if you put a 3, that too is going to give you, is that a 14? So you see how we are moving. These are the numbers. Immediately you get these numbers of pi electrons, and then you make these other rules here, then your compound is going to be aromatic. But for anti-aromatic, if n is 1, that will give us 4. You're moving like in multiples of 4. And then if n is 2, that will be 8. And then 3, that is 12. And 4, that is 16. So if you find these pi electrons, that will tell you what your compound is going to be. So if you look at this ring I've written, which is benzene, it has got 3 bonds. And for each bond, there is 2 pi bonds. So meaning we have got 6 there, and you can see 6 is falling on aromatic. So meaning that this one is going to be aromatic. And if you look at each carbon, this carbon is only bonded to 3 things. This carbon is only bonded to 3 things. This carbon also, this carbon also, this carbon also. So this molecule is cyclic because each is bonded to 3 things, meaning that it is sp2 hybridized. And you can see the bonds are alternating, so that is conjugated. And the molecule is going to be planar. You can see we don't have any bonds which are like so, bonds coming in front of us or behind us. In other words, the molecule is not in 3D, it's in 2D. Okay, and then it has met our formula of the alkyl rule. So let's say we look at a compound like this one. Want to find out if it is aromatic or not. Now for a compound like this one, the first thing is look at, is it cyclic? So we have met the first rule that is cyclic. Is it sp2 or sp hybridized? Each atom should be sp2 or sp3 sp hybridized. If you look at this carbon, just is bonded only to two things, meaning it is sp2 hybridized. This one is also sp2 hybridized. This one also is sp2 hybridized. This carbon also is sp2 hybridized. And then look at the nitrogen. Now, as you can see, nitrogen is bonded to hydrogen. So it's bonded to nitrogen. It's also bonded to another carbon this side, bonded to another carbon this side. So meaning it is only bonded to how many things? Three things. So the hybridization here is sp2. And when you see a lone pair of electron, a positive charge or a negative charge, that represents a p orbital. And the p orbital is the same as a double bond that you can see. So that is representing conjugation. So remember, your molecule should be conjugated. Double bond, single bond, double bond, single bond, double bond, single bond. So already we have made that all the atoms are sp2 hybridized. Now is your molecule conjugated. So you take a lone pair of electron as a double bond. Even when you have a positive charge on a compound, you take it as a double bond like that. So this is the double bond, single, double bond, single. So you take the lone pair as double bond, single. So you can see this molecule is also conjugated. And then how many, what formula are we obeying for this molecule? If you look at this lone pair, that lone pair is representing a pi bond because there is an hybridized p orbital. So that is one pi, we have got two pi bonds there, and then two pi bonds also in this one, two pi bonds in this one. So that is 6. So that has made this formula. So this compound here is aromatic. Okay, it is aromatic. I'll give another example just to make sure that we get this through. It's important to understand this. So say we have been given a molecule like this one. Okay, so if you look at this molecule here, say it has a positive charge at this point. The first thing we need to make sure we meet is it cyclic? We can see it is cyclic, so yes. Are all the bonds sp or sp2? If you look at this carbon here, it is bonded to three things, meaning it is sp2. This one sp2, this one sp2, this one sp2, this one also, this one also. How about this carbon? Now you can see this carbon is having a positive charge. The meaning of a positive charge is it only has one hydrogen attached to it. So it has got a deficit of electrons. And when something has got a deficit of electrons or more than one electrons, that means that there is a p orbital that is empty. So this compound has got a p orbital that is empty, and for that reason it means that it is also sp2 hybridized. That's the only way we can have a p orbital that is empty for it to have that positive charge. And then is your molecule conjugated? So if you start from where you have got a double bond, you should have double, single, and just like that. Okay, so we'll start here, double, single, double, single, double, single. And then this positive charge of the carbon will represent the double because of the pi the p orbital that is unhybridized, and then single. So you can see there's an alternating of bonds. So meaning that this molecule has met also the conjugated system, and it is also planar, right? It is in a plane, like it is in a 2D shape. So meaning that, let's count now, does it obey the Haeckel's rule? Let's find out the pi electrons. Two here, two here, two here, and then two here. 2, 4, 6, 8. So that is 8. But if you check on here, does that meet our formula? Okay, so that is not meeting that formula in this case. Let me just count that again. 2 in this bond actually, and then 2 in this bond, and then 2 in this bond. Now, for this one here, you are not going to have 2 electrons because there's a deficit of electrons. So forget about that too. I mentioned there's a deficit of the positive charge there. So this means that this compound is what? Having only 6 pi electrons. And that is part of this formula here. And this means that this compound is aromatic. The last example I'm going to give here, let's say I've got something like this. There's a negative charge here, a negative charge here. Negative charges represent unhybridized p orbitals, meaning that this will represent more like a double bond, even this will represent more like a double bond. So you have got double bond, single, double bond, single, double bond, single. So that obeys the conjugated. So this molecule is conjugated. And this is planar, like it's in a plane, it's in a 2D shape. Does it obey the Haeckel's rule? We only have this one bond here, right? That means it obeys the Haeckel's rule. You can see one bond means 2 pi electrons, and it's also cyclic. How about hybridization? So if you look at the molecule itself, all the atoms are going to have sp2 hybridization. This one is only bonded to 3 things sp2, 3 things sp2. This one also only has 3 bonds with the hidden hydrogen, because there will be no other hydrogen because this is extra bonds there. Okay, there's no bond there because that's what the negative charge means. So I've also obeyed this one. So this means that this molecule is also aromatic. Now if you look at this one with 8 carbons, if you look at the 8 carbons, of course, if you count all these rules which are here, it is cyclic. That is true. It no it's all the bonds, you can see the double bonds are alternating, right? Alternating. So meaning that that compound is going to be sp2 hybridized, and you can see the bonds are alternating. That means that our molecule is conjugated. Other thing is that this molecule is going to be planar. Okay, like it's in a plane, it's in a 2D shape. But the only thing is, does it obey Haeckel's rule? It has got 8 electrons, and 8 is not part of here. So because it has obeyed everything, the only difference is at the end here, meaning that this molecule is and aromatic. I hope that clarifies now everything that we did. Is it okay? Doc, you can just say again what you said. I was connecting something. Yes, yes, that's what you do. All right, so we finished question two, so we're starting at question three. Now here, predict the major product of each of the reactions shown below and draw the structure. Give a detailed mechanism for each of the reactions C and H. So we are only giving a detailed mechanism for C and H. The others we are just writing structures. Okay. So the first one that we have here, we are reacting. Look at this. What do we have? What is this compound that we've been given? This one. Anyone? This one has a double bond with oxygen. So this is how many carbons? One, two, three, four, five. This is pentanone. It's a ketone. Now remember we've been mentioning. So what is going to happen in this mechanism is this. The first thing first, look at what we have. We have got hydrogen cyanide. Okay, hydrogen cyanide. So what can happen is that the bond between hydrogen and cyanide is able to break like so. Now the oxygen can grab that hydrogen and look at what we are going to have. So be a double bond and then hydrogen, so this will become positively charged. Now the cyanide can come in and come and attack here. When it does that, this bond will break, and the product that we are going to have is going to be this. It's a cyanide attached here. So you're supposed just to write the final product, no mechanism required. So this is the thing that forms when a ketone reacts with hydrogen cyanide. And then for the next question, question number two, we have got we have got this compound Cl. We are reacting it with water. I'll write water in this way. Now, this is an acyl group, acyl compound. When you see a double bond with oxygen, a chlorine at one end and the other group at the other end. So what happens is that you can react an acyl group with water, and what you'll be able to form is going to be an acid. So in this mechanism, the first thing that I just want to show the mechanism, but it wasn't required. We've already said we're going to form an acid. So what happens is that this is going to go and attack there. This bond is going to be able to break off. And then we are going to have a single bond like this. And this is going to be negatively charged. The chlorine is still here. Now look, oxygen has attached at this point, and this oxygen has got two hydrogens. It has got a positive charge. Now the next thing that, let me write this one properly. Let me write the hydrogens alone. The hydrogen here, hydrogen here. The next thing that happens is that this oxygen that is here can actually grab a proton here, and then the bond breaks. So we're going to have OH on top there, and then we also have OH down here. Okay, and then in the next step, one of the double bonds with this oxygen is going to come down. When that happens, the chlorine is going to break off. So now we have got a double bond with oxygen, but this oxygen is bonded to a hydrogen, is going to have a positive charge, and then we are going to have OH at the end. The same chlorine that we have released can actually come and grab this hydrogen, breaking off this bond. And that will give us our final product. It is a double bond with oxygen and OH. Is this okay? Is that okay? People, are we together? Okay. Okay, the next one we have here, I've got this compound, NH2, double bond to oxygen on top there. You're reacting with hydrogen and water. If you see this is a ketone or a carbonyl group. This is an amine. When you react when you combine an amine and a carbonyl, you form an amide. So this is the amide functional group. When you react an amide functional group with an acid in water, you still form a carboxylic acid, just like the previous one where we're forming a carboxylic acid from an acyl chloride, okay, an acyl group using water. So it's the same. Now in here what will happen is that the first thing is we are going to grab a proton. You can see we have got a proton in this solution. So we're going to get this proton. So now we have got this with a positive charge. Then we have got the amine. The next thing that happens is now our amine is going to come in. Sorry, not our amine, but our water will come in. So this water will come now and attack at this point. When it does attack, the bond on top there is going to be able to break off. Oh, it's now a single bond, not a double bond. Remember, it's attached to oxygen, so that is OH. And then down, we are also going to have oxygen, but this one is bonded to two hydrogens. Are we okay up to this point? Remember, they said that for C and D and H give a detailed mechanism. So this is a detailed mechanism we're writing. Are we okay here? Okay. And then another water molecule is going to come in to remove this hydrogen. This bond will break off. So I've got NH2 at the end here. We have got OH on top. So we have got OH also down. At this point, this nitrogen has got a lone pair of electrons. What it does is that it can grab a hydrogen which is in solution. This bond will break off with water. So now I've got nitrogen bonded to three hydrogens. So it will be positively charged. The aim of that is we just want to make it a good living group. Okay, like that. So at this point, when we have formed this nitrogen, it's now ammonia. It's now a good living group. Then one of these bonds can break off from here to come and form a double bond, and then this group can break off. So this is what we're going to have. So now we have got a carbon here, carbon, another carbon, now a double bond with oxygen. This oxygen is also bonded to a hydrogen, so it will now be having a positive charge. And then we have got it, OH. Is this okay? So be free to ask please if you are not good at any point. So at this point now, we are going to be able to remove this hydrogen. Okay. we'll be able to remove that one hydrogen that is here, that bond. This bond will break off and go here. So now our final product is this, which is an acid. So that is how we form our acid at this point. Remember, it was right a detailed mechanism for this one. Does that make sense? Okay. Okay, so now we've used the water molecule to remove the hydrogen which was on our oxygen there. It was OH, one lone pair had to move down. That formed the double bond pushing away this group. Is that okay? Alright, so for the next one here, we want to also write, look at what we've been given. Now this compound that we have is not different from the previous one that we have done. Actually, the mechanism is going to be the same. So what we are going to end up forming, we'll end up forming an acid. Okay, it's the same mechanism as the previous one. The hydrogen here is going to be grabbed. That's how we started also from the previous one. When that happens, look at this. But the double bond there with the hydrogen, that is going to have a positive charge. Then we have got OR at the end here. And then in the next step now, remember we have got water as a second reactant. Water is going to come in. Water comes and attacks here. That breaks off this group. So I've got OH and then water is attached here. Anyone to guess what is going to happen next? Anyone? Yeah, so we remove this hydrogen. The bond breaks off there. And then, what do you think is going to happen next? It's the same mechanism, we're just going through it again. Anything? So what can happen is, just from the previous one, we are converting amine to a good leaving group. We can as well convert this one to a good leaving group by grabbing a proton that is in solution. Say we grab a proton, this oxygen grabs a proton. This proton can come from protonated water. So we have got oxygen bonded to R, it's also bonded to H. It's now positively charged. It's a good leaving group. So again, a lone pair here can come, break off, come in to form a bond here, and then this group now can leave. So I've got OH. So this will now be a double bond with oxygen. And there's going to be a positive charge here. The goodness with chemistry, if you understand really a mechanism of one, you know the mechanism of a lot of things. So here again, water can come and grab this proton. This bond will break off. And that is how we end up forming our carboxylic acid. So that will be the final product. So remember, we just wanted the product and not the mechanism for this. The next one here, now look at we have We are reacting this with some sulfuric acid. And we know that sulfuric acid can react with alcohols, converting them either to alkenes or ethers. Can also convert them to compounds that have got the SO group, this one. But this one is dependent on temperature. Okay, which one of these we are going to form is going to depend on temperature. But what is the first thing that happens? Hydrogen from the sulfuric acid is going to be grabbed by the oxygen, and this bond is going to break off. So I've got this one with a positive. It has two. It has got two hydrogens. So at this point, this bond can get to break off. So we are forming this one with a positive charge here. Now, if it is to form an alkene, the alkene will be very unstable because the only alkene that we can form is to put a double bond here. But look at how the double bonds are arranged. That will really be unstable for the alkene if we are to form for this compound. Now, the other chance is that we can form an ether. Now, an ether is we connect this chain to another one of its kind. So put oxygen here and then we write this chain again. Remember, this one has got this group somewhere here. So that would be the ether that would form. Now, I don't even know the temperature for this molecule, so that would be one possible product. But I believe what will be more stable is you getting to attach the SO. So the same molecule that you had released at this point, SO3H, worked as a nucleophile coming to attach at this point, so that it can become our product. Actually, I've not written the bond rightly. So I'm supposed to write a bond like this. We're not attaching just direct to the ring. There was already a carbon there. Then for the next one here, look at what we have. A double bond with oxygen here. What are we reacting with? We're reacting with this group. So first thing is going to be able to identify what the group is here. Okay. So this is C6, 6 carbons H5. Most if you see C6 and H5, you should think of a benzene ring. And then you can see it's bonded to NH, so bonded to a nitrogen, which is bonded to a hydrogen, and then to NH2 again. So this nitrogen is also bonded to nitrogen with two hydrogens again there. Now, one thing that I want us first to take note of this one is when you're writing a carbonyl group with a compound like this, with this compound, you're writing a carbonyl group. Let me first give a general carbonyl group that you can use. Let's say we have got a compound like this. It has a double bond here, and then it has got R here, another R. So I've got R group, and then another R group. So this one is near because it can be if it's an hydrogen, then it's an aldehyde. If it's any other group, then it's a ketone. So in this mechanism, when these two guys react, what you expect to form at the end is, on the first step, let me write it at the beginning so that it makes sense. We have written it here, we might not be able to follow. So what is going to happen here is that in the first step, we are going to get our ring. We will be able to attach this group that we have. So we'll be removing those nitrogens that you're able to see there. Okay. So look at this. You're going to have your bond with the nitrogen. You still have the hydrogen on top there. Let me write the hydrogen down. And then that is bonded to a nitrogen. Now when you see one nitrogen, the two hydrogens are going to be lost here. Okay. But we are going to form this double bond that you can see with this our group is the one that you are going to be able to see here. And then you see now your R2 bonded at that point, and then your R1 bonded at this point. So that's the first group that we form. But then the final product that we get to form in this mechanism will be, we still have our ring. That is bonded to a nitrogen with a hydrogen down here. Now next you'll not be able to see this nitrogen. So in this step, on this step that I'm writing here, you lose an amine and then you add a proton. So we're going to lose an amine in nitrogen with 3 hydrogens. How are you going to know the molecule that has been formed? Look at the nitrogens that we have. So for these, I mean the arrow groups that we have got the first one and the second one. So simply get this carbon where the R2 is bonded direct there, okay? And then this other carbon here where the R2 is bonded. So these guys are going to form, these are the ones which are going to be directly bonded to your nitrogen and directly bonded to this other carbon here. Okay, so this is the carbon 2, this is the carbon 2. This is the carbon 1, this is the carbon 1 here. That is what happened. But those who are connected directly, remember, so I'm going to connect them here. Now when you connect them, we form a double bond between these two. And then this is our R group this side. R2, sorry, this is R1, this structure here. And then our R2 is going to be here. So we end up forming something that has got 2 rings at the end of it all. So that is what I want us to take also with this structure that we've been given. It's also a carbonyl group. You can see the only difference is that there is a ring. So let me put a double bond here. I want us to follow what I've written on top here. So the first thing you write your ring that has got the nitrogens, that's got alternating bonds inside there. This one is bonded to a nitrogen and a hydrogen. It's going to be bonded to another nitrogen, which is this one. Remember we said the 2 hydrogens at the end are going to go. And that is where we're going to attach our what? Our compound. But we attach at the point where there is the double bond. Hope that makes sense. We are attaching at the point where there is the double bond, just like we did with this one on top. I want to use that one because so that we are able to follow this. You can see this one at the double bond with oxygen, that's where we're connected. So same way with this structure where there is a double bond with oxygen, that's where we're going to connect at. So write a double bond like that, so, and then we write our ring. Are we okay here? Are we okay? Even if you are lost, it's better you say something other than being quiet. Okay. Don't worry, you come through, you go through it again. You hear my voice again. So what is happening next? Remember, we said that the 2 carbons which are attached directly to our ring. Let me just write a product so that you come and go through. Now I need to explain so that you'll be getting my voice when you're going through. Pray that this one doesn't come in the exam. But anyway, you need to still know it for whatsoever case. So it's not hard, docs. Look at this. Look at what we did. We just got our compound that we are given. We removed the two hydrogens which are there. And then at the end where there's a bond with oxygen, we remove that oxygen and that double bond, we just put it on top of the hydrogen here. That is what we have just done. I've not changed anything here. Nothing any hard. Is this still confused? There's no need of a mechanism here. You are just writing. You just want to derive the product. So I'm just showing one intermediate that will help you to reach to the product. There's no need of a mechanism. It might be more complex than this. It's actually more complex than this. So you are just getting your compound, putting it on top. Just getting this oxygen, putting it on top of the nitrogen here, and removing the two hydrogens. That's all. Is that okay? Okay. And then I've got nitrogen that is bonded to a hydrogen down. Now remember the next thing that we said was you look at your compound here, right? This double bond is bonded to a group this side, also bonded to a group this side. So what you do is that you are going to think of this as your R1 here and your R2 here. So you have got, you want to leave two carbons between R1 and R2. So I've got this carbon here, because you are going to use this to connect to your ring. Okay, so what you are doing is that you are going to get those two carbons I've labeled as R1 and R2, but now this nitrogen is going to be lost. You are going to bring that carbon I've labeled 2, that's the one here. That carbon I've labeled 1, that's the one that you connect this side. This is the carbon I've labeled 1, carbon I've labeled 2. And then simply connect these two. And then join the rest of the molecule. You can see I've got this carbon, you write it there. I've got this carbon, you can write it there. I've got also this carbon, you can write it here. And then connect at the end. I know it's trick. I know. Okay, so let's answer this one. This is the one they require that we write a mechanism. This is the one that they've given in their classes, not this one. This one they've not even taught, so they just brought it. So don't feel bad because of one question which is looking bad. Look at what we have. What reagent is this? We talked about this already. What reagent is that? In this class, no one knows the reagent. Maybe you can see it is C6H5MgBr. Anyone? So it's a Grignard reagent. So we said that for the Grignard reagent, these two guys will not affect anything. We just delete them. And then this carbon will remain the negative charge. Okay. Now remember, I want to write a detailed mechanism. Oh, this is not actually the one we're writing the detailed mechanism for. For the Grignard reagent, we form alcohols. So what will just happen is that this guy will go and attack this carbon. This bond will break off. So this is attaching here. Now in case you don't know, C6H5 is a benzene ring. And then remember at that point we also have an oxygen, so to have a lone pair. But that lone pair will grab the hydrogen in solution, so you form an alcohol. So this will be your product here. Okay, that's the compound that you are going to be able to form. So this is the one they asked us to write a detailed mechanism for. So we had taught about this mechanism, the addition of an alcohol to a carbonyl group. If you follow our tutorials, you'll be able to see it. Addition of an alcohol to a carbonyl group. So in the first step, what happens, we are going to use our sulfuric acid, which is down here. The oxygen will be able to grab a hydrogen, breaking off this bond. So now we form this, and the oxygen is going to have a positive charge because it has got 3 bonds. It is still having a hydrogen here. Now in the next step, our alcohol, which is on top there, please you need to know this mechanism. Okay, you need to know what happens when you react a carbonyl group with an alcohol. The alcohol can now come and attack here. So what you are going to form is first a hemiacetal and then an acetal. This bond will break off like so. So we're going to have OH, hydrogen. Now look at this. You have got oxygen bonded here, OH here. Remember this had an hydrogen. So this will be positively charged. Now we'll use, let's say, at this point we remember I produced OSO3H minus. So this same guy can come in and remove this hydrogen here, and that breaks off this bond. So I have hydrogen, we have got OH, then we have got oxygen, with another oxygen there. Okay, so what we have formed here is known as the hemiacetal. So hemiacetal is a compound where I've got a OH and an ether. Okay, now for this mechanism you need to know that another alcohol comes in, but then for this one the other alcohol is itself. So if there was no alcohol function group at the end there, would have used another one of the same molecule that had attacked earlier. Take note of that. Okay, but then before then what will happen is that the oxygen that is on the bottom here is going to grab a proton. It can grab from another sulfuric acid. So this will grab a proton, breaking off this bond. So we have now oxygen with 2 hydrogens like that, and then it is bonded to oxygen, which is bonded to OH. Now at this point that we have reached, that is when the alcohol can act again as a nucleophile. Let me pause a bit. Are we good? Are we good? We are lost from somewhere. Okay. Before the OH attacks, in this, please you need to take note of this. After you formed your hemiacetal, and then you have formed your protonated water, one of the oxygens that you initially added in from the alcohol is going to send its bonds to form a double bond, and that will break off this compound. So this is what we have now. Oxygen, this will be a double bond. Then we have got this group or H at the end here. So that is what happens. Now at this point, that is when you have formed a double bond, that's when another water molecule comes in. And this other water molecule will be from itself. So this one will come and attack this carbon. Same carbon having the oxygen, the double bond. The double bond will end up breaking again. For this mechanism, I can. Oh, thank you very much. That's true. That's true. That's true. So that oxygen is known to have a positive charge because it has got three bonds. So this one has a positive charge. Now look at what we're going to form. Like that. We now have a single bond with one oxygen, and then we have come and formed another bond with the other oxygen. Remember, the other oxygen that is coming in has got a hydrogen. Between this oxygen and this oxygen, how many carbons are there? One, two. So put those two carbons, one, two, and then you just connect. This oxygen also has a positive charge. The next thing that happens is that you can use the water molecule to come and grab this hydrogen. This bond breaks, and our final product. I can actually write it down here. Oxygen, oxygen, and then like that. So this will be our product. Okay, that's how we form our acetal. Two ether functional groups. This mechanism you really need to know. Let me do this for practice's sake. Try out this one. You can send on WhatsApp when you find the answer. Okay, we are using these reagents. This one, the alcohol is in excess. Take note of that. Alcohol is in excess. So the other one, the same alcohol had two functional groups, so it attacked and attacked again. But here the alcohol is in excess, meaning if it attacks and then to come and attack again because it's not the alcohol functional group is not in the same molecule. Please try out this question. Alright, so that is this. The next question. A compound A C5H12O does not give a precipitate with phenyl. Now, let's remember, if something does not give a precipitate with phenyl, what does that mean? What does that mean? Is it that everyone in class today does not attend our classes every day? Okay, no precipitate with phenyl. Remember, A has got the formula C5H12O. No precipitate phenyl means that there is no carbonyl group. Because phenyl is a test for carbonyl groups. Oxidation of A with potassium dichromate gives B. So when we oxidize A, we get B, and this is oxidation. And what we are using here is potassium dichromate. It's giving us B, which is C5H10O. Compound A reacts readily with phenyl. That statement means that this one has a carbonyl group, but does not give a tolerance test. Tolerance test is positive for aldehydes, meaning that this is a ketone. The original compound can be hydrated with sulfuric acid to give a hydrocarbon C. So hydration of this one, hydration we are removing water, we can get C, which is having the formula C5H10. And then ozonolysis of the compound that you've been given, C, is going to give acetone and acetaldehyde. So if you break down C by ozonolysis, you get acetone and the acetaldehyde. Now I want to deduce the structure for A, B, and C. Already acetone is a ketone, like this, 3 carbons. Acetaldehyde is an aldehyde, 2 carbons, the other one is hydrogen. So what you do is that you can just write these guys well, such that the oxygens face each other. Okay, this. So what will happen is just remove the oxygens and then attach the bonds there. That is going to be your C, the one you broke to give you that compound. So that will be this one. This is C. Now remember, C was formed from hydration when we removed water. What happens if I add back water to this compound? When you react this guy with water, you are going to form an alcohol. When you react a double bond with water in an acid, you form an alcohol. When you hydrate an alcohol, you form an alkene. So the chances are that alcohol can come, the alcohol function group can either attach here or attach here. Those are the two chances. At the same point where I've got a double bond, that's the meaning. Now, if say we had attached the OH here, and then we also attached, this is a hydrogen, don't forget there's a hydrogen there. Let's say we had attached the OH here. This one is a tertiary alcohol. This one is a secondary alcohol. Now we know that A was supposed to be oxidized. Tertiary alcohols do not undergo oxidation. So meaning that this is not a possible structure for A. So the structure for A is this one with an OH here. When we oxidize this compound, simply remove the hydrogen and then put a double bond there. So put a double bond here. Okay. Now the single bond. For A, sorry, forgive me. For A, the double bond is not supposed to be there. When you oxidize an alcohol, it forms an alkene. When you dehydrate an alkene, you form an alcohol. So we are simply removing the hydrogen on A, then putting a double bond with oxygen. So this is going to be our B. So that would be B, that would be A, and that would be C. So that is how we work out those. Okay, let's look at this one. Consider the following two dienes. Explain why 1,3 pentadiene, that is the first structure, gave enthalpy of hydrogenation far much less than that obtained for 1,4 pentadiene. So I want to explain that. So we should be able to explain using a mechanism. Okay. So what can happen is, it's saying consider the two, explain why hydrogenation or adding an hydrogen. I'm starting with the first structure that we've been given, double bond here, double bond here. That is the first structure. In hydrogenation, what you do is you can add an halogen bonded to an hydrogen. Can be bromine, chlorine, or something like that. So any one of these double bonds can attack to grab a hydrogen. Let's say this double bond grabs this hydrogen. I want to use this double bond because if I use this double bond to grab the hydrogen, I'm going to form a primary carbocation, and that is not stable. Okay, so that's why I would rather go for the other double bond. This double bond will still be here. But look at this. If hydrogen attaches at this point, because it can attach at any one point where the double bond is, it means that there's a positive charge that will form at this point. Okay. But this guy can form a resonance structure. What can happen is that the double bond can move up to here. When the double bond moves up to there, what you are going to have, remember you still have the hydrogen here, and then you are going to have the double bond here. Now, when the double bond moves, the positive charge also move. It will jump one carbon from to the direction where the double bond is coming from. So the positive charge will come here. Now, another thing that can happen is that another hydrogen can come in because this is hydrogenation. Okay, could have even used H2, but yeah, another hydrogen is going to come in. So that is the step that you are going to write here. Can now react this with hydrogen gas. And when that happens, where the positive charge is, that's where the hydrogen will come and attach. So meaning the two possible structures that we are able to form is hydrogen attached here, a hydrogen here. There's going to be still a bond here. Another one. Look at this. Another one. The double bond is here. There's a hydrogen here. The other positive charge is at the end. So another hydrogen can be added here. So these are the products that we are getting, right, from the first compound. You do the same mechanism for the second one. But for the second one, both double bonds are at the end. Meaning that the only chance is that the hydrogen, we are going to grab the hydrogen using the double bond at the end. There's no other chance. So if this double bond grabs this, let me even change the color. What we are going to see is going to be something like this. This one will still be there. Now the double bond wants to form something that is as stable as possible, the carbocation that is as stable as possible. So the hydrogen will attach at the end so that we form at least a secondary carbocation, because if the hydrogen to attach here, the positive would be here, and that is very much unstable. Resonance for this one is not possible. Okay. For this structure that I've written here, resonance is not possible. So this means, why is resonance not possible? Resonance is only possible if the positive charge is like just one step away from where the double bond is, if it was here. So this means that this structure I've written here will not be formed. This would be the most stable structure to be formed because it's forming a secondary carbocation. But it will not be formed because there's no resonance that can happen. Instead, the hydrogen, when we grab it, the hydrogen is going to come and attach at this end of the double bond. At this end. And when that happens, where is the positive charge going to be able to go? We can't put a okay, the positive charge is going to like go at the end here. Okay. You see we are still forming something that is more unstable, because if a hydrogen attaches, you always break the bond, the double bond, and then one carbon will always be deficient of electrons. So that is why the positive charge goes there. So meaning that this molecule is forming unstable carbocation, such that even if another hydrogen is going to come and react, what are the molecules that you are going to end up with? We have attached a hydrogen here, we also attach an hydrogen here. So now we can explain why the enthalpy of hydrogenation, we are adding the same hydrogen, but then for one compound, it is much more stable than the other compound. What would be the reason for that? That is because even though these two structures have got the same reaction happening, hydrogenation, using 2 moles of hydrogen for each. You can see we are using 2 moles of hydrogen at this point. Why are we using 2 moles of hydrogen? That is because I'm using 2 moles of hydrogen. This is 1 mole of hydrogen, this is another mole of hydrogen. So when we are using that, to give less enthalpy of hydrogenation for the first one, because it is a conjugated hydrocarbon. Conjugated hydrocarbon will give a more lower energy. Look at this. These are conjugated. The meaning of conjugated is they can form those resonance structures which are going to be more stabilized. Okay. Conjugated systems have got double bond, just double bond, single bond, and then double bond, single bond, and then double bond. That's conjugated. This one here is an isolated system. So it has got a very stable energy for it. It's important to understand that. And then you have got also this question here. Consider the following reactions of 1,3 butadiene. At low temperature, 1,2 addition is a major product. What drives the reaction at low temperature? Now look at this. We might not understand what that 1,2 means. So what that means is this. This is a compound that we have, just like from the previous one. We are going to grab a hydrogen. This bond will break off. We have a double bond here. The hydrogen is supposed to attach at the end so that we form a positive charge here, so that it can be stabilized by resonance. So when this double bond moves up to here, what happens is that, remember you still have the hydrogen at the end here. Double bond has moved here, so the positive charge will now come at this end. Now this bromine which was released now can come in the second step and attach where the positive charge is. So for this one to attach here. For this other one it will come and attach at this end. So if you count the carbon, this is carbon 1, carbon 2. So this is called 1,2 addition. And then for this one, this is 1, this is 2, this is 3, this is 4. This is known as 1,4 addition. Now normally 1,4 addition is less stable than 1,2 addition. Why? Because for 1,4, remember we had a primary carbocation here. But for 1,2, we had a secondary carbocation here. And you know that secondary carbocation is more stable than a primary carbocation. But then, okay, so that is the reason. Now the question is saying at low temperature, you need to know that at low temperature the major product is 1,2. That is what you can see what they gave here. You can see this is 20%, this is 80%. On top here you have got high temperature. Like they gave a high temperature here. That should have been like should be 80 or something. Down here should be have been 40. So look at this. At 80 degrees, the major product that you are forming is, where is it? If I've not swapped these two values, at low temperature, that's where we are forming the major product being 1,2. And you can see for this one they gave 80% as 1,4, meaning that is this is okay. So at 80 degrees the major product is 1,4. Okay, and then this is the product that we have written 1,4. This is the one. It's the same as this structure here. And this is even wrong. This is not 1,4. So the structures that were written here, there was a mistake on the typing. The 1,4 is this one. 1, 2, 3, 4. The one they've written as 1,2 is actually 1,4. Okay, this is 1,4. Yeah. So at a high temperature, I want to state this clearly. At a high temperature, we favor 1,4. Okay. So this is going to be the major product, 80%. This is going to be the minor product. We favor 1,4. The major product is going to be this one. Now they've confused this, so they are confusing me when numbering. Let me change it here. This is 1,4. This is 1,2. Okay. So 1,4 at high temperature is the major product, 80%. And then at low temperature is the 1,2 is the minor. 20%. Now when you lower the temperature, the major product changes. Okay, you can say 1,4 will become the minor product as 20%, and then 1,2 becomes the the major product as 40%. Now the question is, at low temperature, 1,2 is the major product. What would be the reason? So the reason for that is the stability of the carbocation intermediate, which is the secondary carbocation, is the main driving force. Remember we said that for 1,2 we are forming a secondary carbocation. That secondary carbocation is the main driving force at low temperature for the 1,2 substitution. And then part 2 is saying what drives the reaction at high temperature, and name the type of mechanism. So the type of mechanism, this is the, okay, at high temperature, what will be able to drive the reaction is high temperature can be able to break pi bonds, right? Like the double bonds can be broken just because of temperature. And when the double bonds are broken because of temperature, then there is chance for addition of our compound, or actually this is substitution. Remember what is happening is we break our bond, right? We are breaking our double bond. At the end we are adding a hydrogen. This is addition, yes. So at high temperature, what is driving the reaction is just the energy. The energy can break those double bonds, and then we can add our hydrogen, we can add our bromines. Okay, what is the name of this mechanism? It is the 1,4 addition reaction. The 1,4 addition reaction. And then part 3 is saying give both mechanisms for these substituents, i.e. 1,2 addition and 1,4 additions. So the mechanism is what I've written down here. The 1,2 and the 1,4. That's the mechanism. It's just that I just attached direct to the Br, but the Br, when we form those positive charges, was supposed to act as the nucleophile, and then it came and attacked. That's how it attached there. Part 4 is saying why is the 1,4 addition a major product at high temperature? That's not a repetition of question as part 2. Okay. That is because the electrophile can easily attach at the secondary carbocation at high temperatures. Why is 1,4 a major product? Actually, 1,4 we're attaching at primary carbons. This carbon here and this carbon here. So at high temperature, your compound, it can easily attach at the primary carbons because of energy. Okay, that, like, basically that is that. High temperature is energy that is facilitating the reaction. Low temperature, what is facilitating the reaction is just the stability of the intermediates. Provide a mechanism to explain formations of the following products. So starting with the first one, we have got OH at the end, we have got a double bond here. We are writing this with sulfuric acid. I mean hydrochloric acid. So the first thing that happens is that your hydrochloric acid will come in, oxygen will grab the hydrogen, the bond breaks. And then we are going to have our protonated water, the positive charge. This water now can get to break off, and then look at what we form. We're going to have a positive charge at this end. Now what can happen is that there is a possibility of resonance. This double bond can move up to here. That is one resonance structure that we can form. It has come here, so the positive charge will now come at this point. So now at this point what can happen is that your chlorine can act as a nucleophile. If it comes and attacks here, the same chlorine which was released at this point, if it attaches there, then our product is going to be here. And then if the same chlorine came and attacked here, then our product will be this one. So that is this one, which is this one here, then this one, which is this one. So that is how we can get to account for the production of those. Consider the reaction given below. Write the structure of the products of this reaction. State which one is major and minor. So for this one, we are using the Grignard reagent. Now we know that a Grignard reagent, what it can do is that it can convert a carbonyl group into an alcohol. So basically what we have is CH3 just, because it's CH3 bonded to MgBr. The MgBr does not affect anything, so it's just a CH3. This guy is a nucleophile. To come and attack here, this bond will break off. We have got a single bond, and then we have attached our CH3 here. Next thing that happens that, remember down we have got protonated water there, so hydrogen can now come in. I mean the protonated water, we can grab the hydrogen from here, and then we are going to have OH. This would be our compound. Even if I don't write this CH3, we know that the CH3 is here. Okay, so this what we have formed here is going to be the major product. So the major product will be the formation of an alcohol. But then the alcohol is not the only thing that can be formed in this step. Remember, we are reacting with the Grignard reagent. Look, we also have ethoxide there. So what can happen is that ethoxide that you're able to see at that point can also come in the reaction. Okay, no, not the ethoxide, but the same Grignard, the CH3, which has got a minus here. This is a nucleophile. This guy can come and attach where the double bond is. That will break off that double bond. So it has attached here. But then if it attaches here, then that means that there's going to be like a positive charge here. The hydrogen is going to come from the water that we have here that will donate that hydrogen that will attach at that point. So we end up having this molecule. And that will be our minor product. Our major product is the alcohol coming when the Grignard reagent attacks, and then the minor product is when the CH3 acts as a nucleophile to come and just attach at this end. Okay. Write the structure of the products of this so that is, yes, where, oh, the double bond has not gone anywhere, it's still there. Sorry for that. Thank you very much. So part 2, explain the distribution of the products. Ensure you refer to the two types of addition observed in this type of reaction. Explain the distribution of the products. Ensure you refer to the two types of addition observed. So 1,2 addition. So you have got the 1,2 addition, okay, which is a minor product. Which one is a 1,2? We had added the methyl here. We had added the hydrogen here. They are just next to each other. When you add the a group and the hydrogen to two ends of a double bond, you call that as 1,2 addition. So 1,2 addition, that will produce the minor product. And then the nucleophilic attack of the Grignard reagent, that is the one to produce the major product. Okay. The first one actually was An SN2 reaction, that a nucleophilic substitution reaction, where we attached our compound to the double bond, breaking off that double bond. So those are the two types of reactions. I've got the addition of CH3 and then the attack by the Grignard reagent, which is nucleophilic also. The last question here, arrange the following compounds in order of their reactivity towards acyl-nucleophilic substitution reactions. So I want to start with the strongest nucleophile, just going like that. Now when you look at these compounds that we have, you have got you have got all these atoms. The first one, the most electronegative, the most reactive, what you are going to look at is electronegativity. Chlorine is going to be the one which will win due to highest electronegativity. That will be the first one. We know that what comes out next is oxygen in electronegativity. But then you have got a lot of things with oxygen here. Okay. So what will come next is going to be when oxygen is bonded to a hydrogen, it's not that much strong. But when you bond it to an aryl group, this aryl group can be any group, becomes much stronger than bonded to a hydrogen. So this will be the second. And then the third becomes this one because it's still oxygen, and then this one. But then this one here, you can see it is even much more stable because you have bonded to more oxygens. Okay, you have got a lot of, like you have got oxygen which is it's more electronegative, and then there are even more. So this will become the strongest of these all. So when starting to count, this will actually be the first, and then now you start from where I've written one. This will be your one. One becomes two, two becomes three, three becomes four, just like that.